Hi class, this is course 2, lesson 21, prime and composite numbers and prime factorization. Okay, so we need to define prime numbers and composite numbers for us. So prime numbers are numbers that are greater than 1, and they have exactly two different counting number factors. An example would be like the number 2 would have factors of 1 and 2. Those are two different counting number factors. Another example might be 17. Okay, if you think about that, the only numbers that are factors are 1 and 17 that are counting numbers. So basically, the prime numbers, those factors that the prime numbers have are 1 and itself. Okay, so 1 and the number. Those are the only factors that prime numbers have. Composite numbers are greater than 1, and they have more than two counting number factors. So, for instance, the number 9 would have factors of 1, 3, and 9. The number 12 would have factors of 1, 2, 3, 4, 6, and 12. Okay, so anytime you have more than two counting number factors, you have a composite number. Composite just means it's made up of more items. Okay, it's made up of, or could be made up of more numbers. Here is a super important item for you to note. 1 is neither prime nor composite. So the number 1 does not fit either of these categories. That is a fact that you need to know, because you'll get tricked on some of the problems when it says asks you to identify prime or composite numbers on a number cube. A lot of you will think that 1 fits one of those categories, and it doesn't. 1 is neither prime nor composite. So let's list the composite numbers between 20 and 30. Okay, and here's what I would do if I were solving this problem. First, I would list the numbers between 20 and 30. So because they want between, they do not want 20 or 30. So I'm just going to make a list. 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, those are the numbers between 20 and 30. Then I need to double check which type of numbers did they want me to list. They want the composite numbers. So I need to cross out any prime numbers. And sometimes that's more difficult than just figuring out which ones are composite. So what I would do is I would circle the numbers that I know are composite. Okay, now remember, composite numbers are greater than 1 and have more than two counting number factors. Okay, here's a nice tip. All even numbers except for the number 2 are composite, because they all have the number 2 as a factor. Let's see. Well, we know, here's what I would do. I mean, seriously, what I would do right now. I'd look at the ones that are left, and I'd go, oh, hey, 25. I can divide that by 5. So that's composite. And then it might take me a little bit of time to figure out which one I want to go to next, but I know that 7 times 3 is 21, so that's composite. Not sure about 23. 27. 27. 9 times 3 is 27, so I'm going to circle that one. And 29, I don't think I have any facts for either. So 23 and 29 are not composite numbers. All the circled ones are. And that's how I would answer that question. Prime factorization is listing the numbers that you can multiply to get to a specific number that are prime. So we can use a factor tree or division by primes, and I will do both of them here, and you can use whichever one you like. So 48, this is the factor tree. And it doesn't matter which number you start with, your end result will be the same as mine. So I know that 6 times 8 is 48, and 6 is not prime, so I keep going. And I know that 2 times 3 is 6. 2 and 3 are prime numbers, so I circle them. 8 I know has factors of 4 and 2. And 4 is not prime, so I know I need to keep going. 2 times 2, and then this 2. So the prime factorization, you list them in number order. This is just the means to get the prime factorization, the factor tree. This is not your answer. Your answer needs to be the product of these factors in multiplication, and you can write them in number order, just like so. 2, 2, 2, 2, 4 2s, and a 3. And if you use what you know about exponents, you could write that repeated base, 4 factors times 3. If you use division by primes, I'm going to put 48 here, and then you have to pick a prime number to divide into 48. So I'm going to start with 2, and then divide that, and I get 24. And then I know I'm going to use 2 again because it's even, so then I would have 12, and keep going. I would have 6, and still even, so I would have 3. And then you can either continue until you get a 1, or remember to include this one up here. Okay, so your prime factorization again is 2 times 2 times 2 times 2 times 3. The thing here with division by primes is that you have to pick, these have to be prime numbers, where these numbers here, notice we did 6 and 8 and a 4, those don't have to be prime numbers. Use whichever way you like. I prefer prime factorization because it starts at the top of the page and works down. I don't have to try to figure out how far down to be on the page and work my way up. Okay, I won't count it wrong if you do either way, just make sure you get it right. Okay, so we're going to write the prime factorization of 64 and the square root of 64. Okay, so I'm going to start with 64. I'm going to put the number here, and again I told you I was going to use factor trees. 64 I know is the product of 8 times 8, and I know that 8 is 4 times 2, and I know that 2 is prime, and I know that none of these others were, and this 4 breaks down into 2 times 2. This 8 is going to do the exact same thing, 2 times 4, and then 2 times 2. So my prime factorization is 2 times 2 times 2 times 2 times 2 times 2, or using exponents, that is 2, 1, 2, 3, 4, 5, 6, 2 to the 6th power. The square root of 64. So take a minute and ask yourself, what number do you multiply times itself that gives you 64? Hopefully you've said 8. So we know that 8 times 8 equals 64. And since I want to undo that squaring, square root of 64 is going to work me backwards to that one number that I use, and that's going to be 8. 8, so let's do the prime factorization of 8. 8 is 4 times 2, and then that 4 becomes 2 times 2. Okay. So the prime factorization of the square root of 64 is 2 to the 3rd. Okay, and I'm going to rewrite this real quickly down here. So 64 is 2 to the 6th power, and the square root of 64 is 2 to the 3rd power. Do you see any similarity between the prime factorization of 64 and the prime factorization of the square root of 64? Hopefully you can tell that the bases are the same. So the bases are the same. And then what about the exponents? What's the relationship between 6 and 3? The exponents are half. Okay, so 2 to the 6th power, if I wanted the square root of that, then the base stays the same, and we divide 6 by 2, and that gives us 3. I'm going to insert a page here so that I can show you that you know that 10 times 10 is 100, right? And the square root of 100 is 10. Okay, so what is the prime factorization of 100? Well, we just said it was 10 times 10, and this is 2 and 5. 5 is prime, and this is 2 and 5. Okay, and maybe I jumped a little too fast up here. The square root of 100 is what number times itself gives you 100. And we just did that over here, where we took the same number times itself, 10 times 10, and got a product of 100. So if we square root that product, we're going to just work our way backwards to one of those factors. Okay, now the square root of, well, let me jump down here. I'm going to come back up here. This, written in prime factorization form, is the base 2, that's there twice, and the base 5 is there twice as well. So I should be able to use that to jump over here. Remember what we said on the previous slide? Keep the bases, so this is going to be 2 times 5. Keep the bases, and then half of the exponents. So what is half of 2? 1. And half of 2, 1. Now what is this equal? 2 times 5? That's going to equal 10. And didn't we already know that? We did. Okay, so hopefully you can use this knowledge to help you make sense out of this. You don't have to know that the square root of 100 is 10. If you know the prime factorization of 100, you can just keep the bases and half of the exponents, and you'll know what your answer is. Okay, so now we can also use prime factorization to find the greatest common factor. So we're going to use 36 and 60, and we're going to use prime factorization. It's very important that when it says use prime factorization that you do that. Now you might be able to find the greatest common factor using a different method, but we're trying to learn how to use prime factorization. So make sure you do that. So I'm going to use a number tree again, and I'm going to start with 36. And let's see, that's 6 times 6, and 6 is not prime. 2 times 3, those numbers are prime. 2 times 3. Okay, and 60 is going to be, let's see, I like 6 and 10. 6 is 2 times 3. And 10 is 2 times 5. Okay, so if I were to write out this in numeric order, it'd be 2 times 2 times 3 times 3. And 60 would be 2 times 2 times 3 times 5. Okay, now, what numbers do they have in common? We have a 2 in common. We have another 2 in common. And we have a 3 in common. So we're going to write down one of those numbers from one of those sets of numbers. Okay, so we know there's a 2, we know there's a 2, we know there's a 3. So don't write it down twice, just write that down once. Then multiply them. 2 times 2 is 4, 4 times 3 is 12. So your greatest common factor is 12. So here are the rules for doing this, or how it's done. Write the prime factorization of each number, then identify the prime factors that they have in common. That's when we circled. Multiply those factors, just one set of those numbers, and the product is your greatest common factor. So we can use this to help us reduce fractions, and we'll do that in another episode, or in a future lesson. But make sure you write this down and follow this process when it asks you to find the greatest common factor using prime factorization. Okay? We will talk about this in class.